Yes, sir.
It's visible, Rohit?
Yes.
Yeah, good. So this is going to be our 7th lecture of operating system, and specifically the focus of this lecture is CPU scheduling, deadlock, and the multiprocessor scheduling. So it is going to be the first part of this particular focus. So what particular objectives do we have in this lecture? So some of the objectives are that we are going to specifically talk about the CPU scheduling, its types and the mechanism. Means what is the CPU scheduling exactly, and what are the different possible types of assigning CPUs to different processes, and what is the basic underlying architecture and the mechanism that allows this sort of phenomenon, means the CPU scheduling in the system, and some of the related concepts. Additionally, we are going to talk about the deadlock system. Deadlock, as we talked in the introductory session, that deadlock is the condition where the processes are dependent on each other in such a way that none of them is able to make a progress. So that's why, what is the deadlock? When the situation comes up, means what is the exact situation when a deadlock happens, and some of the related concepts that how you can avoid it, how you can prevent it, and sort of things. Finally, we are going to talk about the multiprocessor system. So multiprocessor systems means the system having multiple processors, means the CPUs or the multiple cores. That is also the multi-threaded system. And then what is the possible scheduling? If you do have, means multiple controls are available there. And then there are the different processes who are supposed to get assigned to these different processors. And then you are supposed to perform the execution of all the processes in such a way that all the processes complete their execution in best possible way. And finally, we are going to exchange a few words in terms of question and answers. So starting with the very first topic, that is CPU scheduling. So as you can see from the diagram, that scheduling, not only scheduling means anything. When we say that we are going to do something, we are going to have this sort of work, and scheduling is also some sort of work that your processor, means the operating system, performs. And CPU is the kind of hardware device that is responsible for doing it exactly in an actual manner. So scheduling is supposed to be based on some parameter. That parameter is the criteria. So that criteria is situation dependent. Means in one particular system, you want to maximize the CPU utilization, or you want to maximize the throughput. But at the same time, you want to minimize the turnaround time, waiting time, or the response time of the system. So your scheduling criteria need to be specifically defined. But in most of the situations, we want to get both things. Means we want to maximize the CPU utilization and throughput, and as well as we want to minimize the turnaround time, waiting time, and response times. But it might not be possible in all the cases. But we try to achieve both the good things. So finally, what is CPU scheduling? So when we say, as we told, that scheduling means the decision of assigning processes to CPU. That is CPU scheduling. Means if you remember correctly, then we discussed the schedulers way back. So when we discussed the schedulers, we discussed mainly two types of schedulers, the short-term and long. And in that short-term scheduler is supposed to be kind of called the CPU scheduler, because it assigns the processes from ready queue to CPU. And when those are with CPU, means the processes are getting executed, then the processes are supposed to be called in running state. So what CPU scheduling is? CPU scheduling means the CPU assignment decision. Means you have multiple processes, you have a number of processes, and you are now making a decision that these ready processes are available in the system. Means those processes are in the RAM, obviously, in ready queue. Now you are supposed to choose one of these processes to assign to CPU at a time. Now the question is, which process will you choose? So this question comes with respect to some of the parameters, and the criteria will be to maximize these system parameters and minimize these system parameters that are shown in the diagram. Now, depending on the process, means your job, when something is in hard disk, then it is supposed to be called as job or program, and when it is in RAM, then it is supposed to be called process. So you will choose a particular process depending on its characteristics. Means what is its burst period, means how much execution time is needed to execute this particular job, and what is its priority, what are the supposed to be assigned input, output, and all other related things. So these things you will consider in your mind, and then you will assign a suitable scheduling policy that is best possible for that particular scenario. So criteria, as we just discussed, that it depends. Means there is no single criteria on which you will say that this is the best possible way to do things. And in real life scenarios also, we do have many such systems. We have many such scenarios when we are supposed to have a particular decision that we want to do this particular task. Now, what is the best possible answer? So there is no best possible answer, because it always depends on the situation. It depends on the relevant conditions and the characteristics that we are supposed to take a particular decision. And that decision will be best if we have chosen all the related constraints of the environment in the correct best possible way, and we have considered all the related characteristics of the network, and means the environment factors also. So some of the common terms related to CPU schedulings are the burst time, execution time, arrival time, finish time, and the CPU or IO burst cycle. So in last lecture, we discussed in detail that what is CPU and input-output bound processes. Means the processes spend their more time with CPU, then those are CPU bound. If they are spending more time with input-output, then those are input-output bound processes. But the combination of CPU and IO burst of any process defines the life cycle, means the lifetime of the process. So here, CPU IO burst means the time processes are spending with CPU, that is CPU burst, and the time they are spending with input output devices, that is IO burst. Now, the burst time is the total execution time. So burst time is divided in CPU burst and IO burst, because in its lifetime, a process will perform mainly two operations. Either it is executing or it is waiting for some input output. Okay, so means it is a combination. The burst time is combination of CPU burst and IO burst. Then there is a term arrival time. Arrival time means when the process came into system. Now we are saying that process came into system, and we do know that something means some program is called a process when it comes to RAM. So when the program means the job comes into RAM, means it comes into ready state, then that particular time moment is called the arrival time. Okay, then what is the finish time? Means when the process got completely executed. So that is its finish time. So execution time is this one. Finish time minus arrival time. That's it. That is its execution time. And obviously, in execution time, there will be means it will be the combination of CPU IO and as well as the waiting time. Because it might be the case that some process came into execution, and then due to some interrupt or some IO request, it is supposed to wait for some particular period of time. So, you go for some delegated task, you go in bank. Okay, so what is the amount of time that it takes actual transaction or whatever behavior you want to do there? So that is just a moment of time. Means you give your passbook or you do some sort of transaction, you talk to somebody. That keeps or that takes just a fraction of the total time that you spend in the bank, because you go, you wait in the queue, and like that. So many things happen in the system. The actual execution takes very minimal time, but so many related activities like the input output or the waiting time is supposed to be much more in most of the cases. But it is not the case in all the conditions. So that's why we divide the process into categories, that CPU bound process or the IO bound processes. Moving forward, now we are going to talk about the scheduling types. Okay, so as we discussed that processes might be assigned to CPU, then they come into execution state. So execution state means what? That they are getting executed, it means their processing is being done. Now, due to some interrupt, if they switch on to some another location or deliberately based on the scheduling algorithm, processor keeps one process in waiting state and takes another process for its execution. like it is performing the execution in round robin system or something like that. In that case, you are supposed to preempt the first process. Preempt means what? Preempt means you are taking the resources from a particular process. Preemptive. Preemptive means something that can be taken for granted. If we say in loose terms, then we can define it like that. Means if something is considered to be okay, this is not so much importance, and you can execute it at your ease. So in that way, if you consider something, then obviously you are executing it, you are stopping it, and you are giving resources to that process, and you are taking back the resources. So it depends on your choice, means the system or the operating system choice. So those kind of processes are preemptive. But on the other hand, there is a second category, that is non-preemptive category. Non-preemptive means once you have allocated the resources, or once you have assigned the process to the CPU, then you cannot preempt that particular process. Means you cannot take the resources back or the CPU back from that particular process until it completes its execution in normal sense. But there might be some scenario that non-preemptive process needs some sort of input output. So it is not like that you will not give input output. Obviously you will give input output. So in that particular time, CPU will wait for that particular execution process. It will take the input output, and then again CPU will get allocated to that particular process only. Means until the process, if we say in general terms, then non-preemptive process is not supposed to leave the resources until it completes its execution. But the reverse means in case of preemptive, same case is not there, the reverse is there. Means you can take the resources back at your ease. So now the concept of preemptive is clear, that it is based on priority. Because when we say that we can take back the resources, so what is the situation that you are supposed to take back the resource? Because something more important came into system. And if something more important came into picture, then obviously you are supposed to leave the current process and you are giving priority to the more important thing. So that's why concept of priority comes in preemptive system. Additionally, the system is supposed to be flexible, because you are given your choice. Means you are in ease that you choose that which particular process you want to execute first. So like the scheduling algorithm is kind of flexible. Third one, that CPU utilization is bit high. Okay. CPU utilization is bit high. Why? Because processor or the resources are not waiting for one process. Okay. If one process is going for input-output activity, then processor will jump onto another process, and another process will get executed. So processor is not sitting idle for one particular process to complete its input-output. Okay. But in case of non-preemptive, if one process that is non-preemptive in nature, if that process went for particular input output, then processor is supposed to wait. So that's why CPU or the resource utilization is bit low in non-preemptive. So in non-preemptive, resource utilization is low. Concept of completion is there, not concept of priority. Means you are supposed to first complete the task that you are executing right now. Secondly, it is not flexible, obviously, because kind of first in first serve. Means if whoever the person came first, you are supposed to serve that particular person. It is not that first one is the normal person, second is the PM, then you are supposed to give priority to PM. No. Preemptive means you are supposed to give priority depending on the situation. But in case of non-preemptive, you are not supposed to give priority. You are just supposed to do the plain task. Means first come, first serve. No priority at all. Okay. So when we say that we are doing scheduling, so like we discussed a scheduler way back. So at that particular time, we discussed a scheduler so that they are supposed to take the processes from ready queue and supposed to assign to processor. Then there is a concept of dispatcher. What is the concept of dispatcher? Dispatcher performs the context switching. Okay. And it switches to user mode, and then it finally moves it to the correct location in the newly loaded program with the help of program counter, obviously. Okay, so we are going to discuss dispatcher in detail in coming slides. So we move forward, and now we see the CPU scheduling mechanism here. So here you see that what things we discussed just in short in previous slide, we are going to discuss in detail here. So dispatcher diagram is shown here. Now in different books or in different blogs or in different writings, you can find the different definitions or the kind of related terms. Because when we say that this particular component is part of something, then it becomes somewhat subjective. For example, many people consider that dispatcher is something different of scheduler. But many people consider that dispatcher is a part of schedule. So what diagram is here, it's showing that dispatcher is a part of schedule. Because you can see that firstly, some process came from other states to ready state. So that's why it became ready process. Okay. Some other states means the process might be in waiting state or in some input output state or something like that. So process came from other state to ready state means now it is ready to get executed. That's why it became a ready process. Now you will enqueue it. So there is an enqueuer, means bit of utility that is supposed to make it ready to dispatch to process. So there is a ready list. Once it passed through the enqueuer, then it comes into ready list. And now it is the duty of dispatcher, means the software program that is supposed to perform a context switch. Why context switch? Because if you are supposed to start the execution, you are supposed to jump onto the next location where the current means the next supposed to be executable instruction is present. So context switch will fetch the components from program counter and will give to CPU. Because CPU is not something that is supposed to take care of the memory and all these things. The simple thing of CPU is this, just it is supposed to execute because it is the processing element of the system. Okay, so when the process gets assigned to CPU, it becomes the running process. So you can see that what dispatcher is doing, that it is taking the ready process with the help of enqueuer, and then it is assigning to CPU with the help of context switcher, means program counter and all those things come into picture. So here what the term is that what is the difference between scheduler and dispatcher? So different opinions are there. So it depends that you may say that there is something called dispatcher, it's part of scheduler. Okay, and some people do consider that dispatcher is different, scheduler is different. Then they say that scheduler assigns things to processor and dispatcher is a kind of things that takes back from CPU. Some of the people define it like this. So in different textbooks or in different sort of blogs, you may find different definitions. But go with one sort of definition. Normally, what we say that dispatcher is responsible for assigning jobs, means processes. Those are in ready state to CPU. That's why it is supposed to take the processes from ready queue and it is supposed to assign to CPU. That's why processes become running process. Moving forward, we are going to discuss some of the CPU scheduling algorithms because we understood till now that what exactly CPU scheduling is and how it is going to work. Means CPU scheduling means processes are supposed to get assigned from ready state to running state. But how the scheduler or how the dispatcher is deciding the criteria, so that is not visible till now. So that's why we are discussing the CPU scheduling algorithms. As you can see, there are multiple scheduling algorithms here. So first come first, the shortest remaining time first. Okay, shortest remaining time, some people call it like that SRT, or some people call it like shortest remaining time first, means SRTF. And some people call it a shortest remaining time next, means the next process that is supposed to be assigned to processor is having the shortest remaining time. So SRTN, but that shortest remaining time first or shortest remaining time next, all these things are dependent on a specific culture, whatever you are calling to a particular kind of scheduling. But one thing is clear, that your criteria is clear, that whichever process is having the shortest remaining time, that you are going to assign to process. Okay. Then third one is the priority based scheduling, quite clear with the name, that there is a priority factor assigned with each of the processes. And then you are supposed to assign the process to the CPU based on their particular priority. Now, priority definition might be different because when we say priority, then it becomes so subjective that higher number is having more priority or lower number is having more priority. So like in class, if you are supposed to choose the best scholar, then whoever scholar secured the most of the marks, then that particular scholar is supposed to be the best scholar, if that is the criteria. Okay, so then more marks means best student, means that is the priority, means highest priority. More marks, highest priority, means larger the number, higher the priority. But you consider the other scenario that you appeared for some exam and then you got some rank. So lower the rank, better the person, means lower the rank, higher the priority. So in the similar way, normally second concept is considered that when the number is lower, means when the priority number is lower, the priority is more. Okay, but it is always subjective. So when you attempt for any question or something like that, then carefully read the question that how the priority is defined in that particular question. Then the concept is round robin. Round robin means you are supposed to roam in a cyclic fashion, means you are supposed to round like a robin does. So in a round robin fashion, we are supposed to assign processes to CPU after a particular time quantum. So there is a concept of time quantum here. Time quantum means a time period. For example, you assigned a time quantum of 2 milliseconds. So for each of the processes will get assigned to processor for 2 milliseconds. Okay, so for 2 milliseconds, whatever is the process that is supposed to be executed with the CPU, that will get executed, and then there is the chance of another process. So in this way, there is no kind of starvation kind of thing, means every process will have a fair chance for execution. Then there is a concept of shortest job first. Okay, so shortest job first and shortest time remaining time. Both things look similar. So can anyone of you tell me what is the difference between these two? Just read the name of the scheduling algorithm and tell me, means just with the name only it becomes clear that what the underlying semantic is there. So can anyone tell me what is the difference? Shortest job first, shortest remaining time.
Professor?
Yeah, Nikhil.
So I think like shortest job first is you look at the total time from start to finish.
Yeah.
Whereas shortest remaining time is if somehow the process had been stopped and then paused.
Yeah.
And then now you decide like of the paused remaining processes which has the shortest time till completion.
Yeah, great. So what exactly Nikhil is trying to say, that we are supposed to just consider the time which is remaining, which is remained until its completion. So that is shortest remaining time. Because for example, a process is supposed to have 100 millisecond time for its execution. Okay, so that 100 millisecond is the total burst, means that is the total execution time. But 90 millisecond have already been completed, means 90% execution is already being done by CPU. So remaining 10 millisecond is there. But there came another process, that is shortest job. Means if we go by shortest job first, and there is another process that have a total lifespan of 8 milliseconds. So then we will assign the 8 millisecond job first to CPU because it is having less time in its completion. So shortest job first means that is having the shortest time in the system. And in the shortest remaining time, we will only see the remaining time. So in shortest job, total lifetime. In shortest remaining time, only the remaining time. That's the difference. Lastly, there is a multiple level queue scheduling. Multiple level queue scheduling kind of you will maintain multiple queues in the system. Multiple queues you will why means the question comes why do we maintain multiple queues? Because processes in the earlier systems we were not supposed to maintain the multiple queues. So point is that each process is supposed to have different characteristics. So depending on their characteristics means there are supposed to be their length or their some of the input output or kind of device they are supposed to get access from or they are supposed to access to. So all those characteristics might be different. So depending on process to process, all these things will vary. So we will create a bunch of processes having the similar characteristics. Okay, and then we will maintain the different queues. Because a particular why we do this, because For example, a particular out of 100 processes, 10 processes are supposed to take input from keyboards, 10 processes are supposed to take input from particular kind of mouse click or event. And then there are some of the processes, those are supposed to wait for another processes, or they are supposed to wait for a particular memory location. So if there is a particular kind of group of the processes, underlying process, then you can simulate their behavior in such a way so that the overall performance of the system gets improved. Because you do know that if some process is supposed to take input from keyboard, then at least there is a delay. There will be a minimum delay of 2 milliseconds. Why? Because user will type something. So it will take minimum 2 milliseconds or 5 milliseconds a delay. So some sort of analysis means some sort of heuristic is already available with the system in terms of the past behavior or whatever data it has. So then you can define that in this way we should schedule. So that's why you will maintain different queues, and in each queue you can assign different scheduling algorithms. So then it becomes a kind of hybrid system, and then you can start execution based on the specific priority. So we are going to discuss the comparison of some of the very common scheduling algorithms, because we till now we have discussed the underlying concept of each of the scheduling algorithms, and now we are going to compare these algorithms with each other based on certain parameters. So what are those parameters? Some of the parameters that first, a very basic parameter is throughput. So can anyone tell me what is throughput? Anyone?
It's some notion of yield. I mean, how much of processes are being completed in a given time.
Okay. So I'm reaching to you guys late, or there is some sort of lag in the system?
No, Professor. Like, there's no lag. It takes a little bit time to think and frame an answer.
Okay, no issue. So throughput is, Archita, as you told, it's totally correct that in a particular fraction of time, means suppose there is a unit time interval. So that unit time interval might be different system to system, because the unit is always system dependent. Okay. So suppose you defined a unit of 10 milliseconds. So number of processes got completed in 10 milliseconds is the throughput of the system. But there is another system that defined that there is a unit time interval of 1 second. So means 100 milliseconds. So then number of processes completed in 1 second is the throughput of the system. So throughput means obviously if we are comparing different sort of scheduling algorithms, or we are comparing any techniques, different techniques, then the underlying criteria means the throughput criteria, the unit time interval will be same for all. So then we are supposed to see here that throughput may be low if quantum is too small. And that in case of round robin, and in case of FCFS means first come first serve, it is not emphasized. So firstly, let me tell you the full form of these terms that is written here. First is quite clear, that is round robin. Second is first FCFS, that is first come first serve. Third is your multi-level feedback queue, that is MFQ. And fourth one is shortest job first, that is HGF. And last one is the shortest remaining job next. So as I told in the last slide here, that shortest remaining time. And in some of the text, you may find that it is written like this, that shortest remaining time first. And in some of the text, it might be shortest remaining time next. So what we are seeing here, it is shortest remaining job next. Okay. So instead of calling the time next, or they have called here job next. So normally, first thing, that time is the most important, because when we are saying shortest remaining job means what? It is not the shortest job, it is the remaining time job. So that's why I'm saying that if you go for multiple kind of articles, then there might be multiple kind of acronyms or sort of definitions that they have taken into consideration. But if you go for a specific standardized textbooks, I'm giving many times in the slides, you may see that some of the references that I do take, I try to incorporate the content from a wide variety of sources. And the reason is because some of the whatever means pictures or kind of literature or kind of text that I am supposed to put here, that is from very wide sources, means very loose sources, kind of blogs. That also from non-even from secure sites, and some of the standard source, that is from some very standard books like Galvin, Stallings, and kind of. So point is that when we cover very wide sources, so then we are supposed to get the wide level of understanding of authors, and it is very important. Why? Because there is always an open audience. When there is always an open audience, there is a bunch of students and they are supposed to go online, they are supposed to read something. Then they are supposed to take input from very wide resources. Then you cannot control their behavior. So in real time, they will encounter multiple terms. Those are never even being discussed in class anytime. And it might be the case that many of the terms that I discussed, I tried to incorporate most of the terms, but still there might be many of the terms that I have not discussed, and you will find them. So don't consider that that particular term is wrong or something. It might be the case that particular author might be trying to deliver something else, or that particular author has defined the same concept, but with a slightly kind of modified name. For example, you can see here that here it has written SRJN. But the nature of this particular scheduling is the same, of shortest remaining time, because shortest job first is just next to this particular scheduling. Okay, so don't go with a particular kind of acronym or something. When you want to follow a particular kind of nomenclature, then go always for standardized books. Okay, so the 3 books that I have told you, out of those 3 also I will recommend to go for Galvin. Okay. Now discussing all these things. So first point, throughput. That throughput might be low if the quantum is too low. Can anybody tell me that I think the concept of round robin is quite clear, that processor will get assigned to each of the job for the particular time fraction. Okay, means if you have defined that 2 millisecond time, then processor will execute each of the processes for 2 milliseconds in a round robin fashion. Now tell me, why the throughput may be low if the time quantum or the time period for execution is too small? Anybody?
So I think throughput is basically the number of operations in unit time or given time.
Yeah.
So time is in the denominator. So if but the point is now how I'm thinking of it is, suppose there a particular thing requires a time of say 1 second, and if my unit time is only 0.5 seconds, then that operation won't occur itself. So the throughput will be low because my time interval is too small for any operation to occur.
Yes. And okay, it is one of the scenarios. Any other scenario? Okay, fine. No issue. So what you told, that is totally correct, obviously, because if the time fraction that is assigned for CPU execution is too small, that but as you told that 0.5 second, so that particular 0.5 second is not supposed to lie within that particular small fraction. But obviously, if 0.5 second is the total execution time of that particular process, then obviously total process will not get executed, but very little part of that particular process will get executed for 2 milliseconds. But the concept that it is trying to say that if the time fraction is too small, because time fraction is what? Understand, time fraction is the time for which a particular process will get assigned to processor. And if that particular process is assigned to CPU for that particular time fraction. Now in between, nobody will disturb. Means nobody will take the control back from processor of that particular process. So after, if suppose the time fraction is 10 milliseconds, then once the process is submitted to processor, now process will get executed for next 10 milliseconds in a non-disturbed environment. Means there will be no disturbance. There will be no kind of preemption or something like that. Okay. So if you do, as we know, that after the finish of that particular time quantum, processor is supposed to pick the next job for the same time interval, and then after the completion of that job, then processor will pick the next job. So in this way, all the processes will get executed. So whenever the processor is jumping from one processor is jumping, we are saying, but in actual what is happening, that processes are getting assigned to processor, obviously. So just understand the concept. In language, many times we do say that processor is jumping, but in actual the processes are getting assigned. So when the processes are getting assigned to processor, and then after time quantum, they are supposed to wait, because the next job will get assigned for its time quantum period. So then what is happening behind the scene? Context switches, because every time a processor is taking a process, it is fetching the contents of its PCB and then it's starting execution for the time quantum. Then after the finish of that particular time quantum, it is fetching the content of another process's PCB and starting the execution. So before going to next process, processor is saving the content of PCB of first process in memory and then restoring the content of next process's PCB. We have already discussed the concept of context switch in detail with the help of a figure. Okay, so when too many context switch will happen, as we have seen, the condition is what? Condition is that time quantum is too small. So if time quantum is too small, means execution time is very less. But switching is compulsory, because round robin is saying what? Round robin is saying that after time quantum, you cannot continue execution. After the completion of time quantum period, you have to jump to another process, and then that particular process will start execution. So that's why if the time quantum is very low, then execution is low, means execution time is low, and input to output means context switch, storing the content into memory, fetching the content from memory, that is more. So if there is the total execution time of process, for example, you run a particular system for 1 hour, okay, and in that 1 hour, every 15 minutes, if you are switching to another process, the time quantum is of 15 minutes, if that is obviously too large. But if we consider just for example, then 15 minutes, then there are only 4 processes, those are allowed to get execution. Okay, but if we allow a time quantum of 5 minutes, okay, so in that particular case, obviously the number of processes can be covered, those are covered are more, but you can see that there are more number of context switches. So if there are more number of context switches, means there is a more memory handling. If there is more memory handling, there is more pointer handling. If there is more pointer handling, then obviously most of the time, means when the CPU is storing the content of processes PCB in memory and fetching the content of next processes PCB from memory, and in between the processes is doing nothing, means its capacity is getting loose, means throughput will be less. Now throughput, as we defined, that throughput is what? Throughput is the total number of processes those completed in a particular time fraction. So it's a kind of bottleneck, means what is the length of process completion, as well as what is the time quantum that is defined for round robin technique. So if the time quantum is fixed and the process burst length is also fixed, then you can easily define it. But if any of these two parameters is not fixed, then you cannot define the performance of round robin. Okay, but it is very obvious, see it from a layman point of view, means don't go into technical details. Now, after this technical discussion, let me tell you just a plain concept. If the time period for execution is small, then most of the time processor will jump from one one process to another process to another process. So time that is wasted in jumping from one location to another is more than actually executing the processes. That's why it is written here that performance may be low if the time quantum is too small. Second, first come first serve. Obviously, in that particular case, throughput is not emphasized. Why? Because you are supposed to be bounded with the process. Means it doesn't matter which process is coming first. You are supposed to execute it. Okay, there is no other choice. So that's why it is not emphasized. Now, multi-level feedback queue may be low if time quantum is too small. Again, as I told you that you can assign different kind of scheduling algorithms to different queues. So then, obviously, if you have assigned the round robin technique to one of the scheduling, one of the queue of the multi-level feedback queue, then in that case, the time quantum will become a constraint. And the same concept of round robin will get applied to multi-level feedback. Then the shortest job first, then obviously throughput will be high. Why? Because every time we are saying the number of processes completed within unit time. And every time you are picking what? You are picking the shortest job. So obviously, if you are picking the shortest job every time, then there is a probability that most of the jobs will get completed within the defined time interval. So that's why the throughput is more in shortest job first. Now, shortest remaining time first, the same case, again, the throughput will be high. Now, this high and low are kind of subjective. Why? Because it will depend on the process length as well as in which context you are talking. For example, this high, shortest remaining time first means shortest remaining job next. That is in comparison to FCFS, its performance will be high. Obviously, in comparison to round robin, its performance will be high. Its throughput will be high. Okay, so but shortest job first and shortest remaining time, which one is good? If you want to compare, then both are high written here. So for that particular actual analysis, if you want to go, you have to go for some sort of practical, because actually you have to define the process length. Then actually you have to define that their burst means what is the IO burst, what is the CPU burst, and then you are supposed to perform that numerical, and then you will get. Okay, exact analysis will come from practical analysis. Then there is a parameter that is response time. So in response time is what? Response time means when the process came into ready queue, then that is its arrival time. Okay, but even after arrival into the ready queue, process might be in the state of waiting state. Means we will not say it a waiting state because it is in ready queue, but we are supposed to say that it is waiting. Why? Because processor is busy with another process in its execution. So if, for example, 10 processes are there in ready queue, but at a time, one process can be executed with processor, because we are considering the scenario of a uniprocessor system. So there is a single processor and with single core kind of, you understand. Okay. So one process can get executed at a time, but there are 10 processes. Those are ready for execution. So obviously 9 processes have to wait. So if 9 processes are supposed to wait, then those are in ready state, but they are waiting. We will not say that those are in waiting state. Why? Because in waiting state might be the processes which are waiting for some particular kind of input or output or user input. Okay, so ready, those processes are in ready state, but they are waiting for their turn. Like in round robin, they get their turn. Okay, so here, when the process came into system in ready state, and when the first turn means when the first time processor got allocated to that particular process, the difference of these two moments is the response time. You understood? Means you went into a party and the first time you got your number to have lunch or something. That is your response time. You arrived into party and you got something. The difference of these two moments is the response time. First time when the process got executed and its arrival time. The difference of these 2 points is the response time. So see, shortest average response. Okay, shortest average response time if time quantum chosen correctly. Again, in round robin, everything is dependent on time quantum. Okay, so that is highly subjective. Now in FCFS, obviously response time might be poor, not only poor, very poor. Why? Because one process that is in very last of the queue, obviously it will get its turn in the very last, because there is no chance that processor will jump onto next process. It will complete the processes one by one. First come, first serve. So the last process have to wait. Then third one, multi-level feedback queue. Then good for input-output bound, but poor for CPU bound processes. Because in multi-level queue, obviously, as I told you, that multiple processes are there, and those are grouped by their characteristics. Okay, so if processes are grouped by their characteristics, then CPU bound processes, those are supposed to spend more time with CPU, and IO bound processes are supposed to spend more time with input output. So response time for CPU bound processes will be smaller. Why? Because they are supposed to initially get the execution opportunity, because initially they are supposed to get execution, and input output are supposed to initially get input output. So input output processes will wait for particular input output, but the CPU bound processes will directly go to CPU. So whoever is going first to CPU will have the minimum response time, obviously. Third one, shortest job first, good for short processes, but poor for longer processes. Obviously, because we are assigning the shortest job first to processor. So the jobs having shorter lifetime will have less response time, because they will get assigned first to processor. And the shortest remaining time, good for short processes. Similar thing, because if the process is short, then its remaining time will also be short. Okay, so in this way, we have understood these two things, these two parameters. Now, there is another parameter, that is IO bound. Okay, so IO bound. IO bound means input output bound. So when we say round robin, then no distinction between CPU bound and IO bound. And in case of FCFS also, there is no distinction between CPU bound and IO bound. Can anybody tell me that what is the meaning of this particular point? That no distinction between CPU bound and IO bound. Anybody?
So I think round robin just goes one by one through all processes in a circle, and first come first serve will just take whichever process comes first.
Yes.
So irrespective of whether it's a CPU bound and IO bound, it doesn't depend on that, because it's just that the position of it, or when it started, that is more important. Which came first is more important.
Yes.
So, yeah.
Good. That's it. Because obviously the CPU bound or the IO bound nature of the process is not dependent on round robin or the stages. Now, next, that in case of multi-level feedback queue, the IO bound process will get a high priority if CPU bound process are present. Anybody, Abid, or anybody else, explain this point?
Not sure, Professor.
Try. Say something. Doesn't matter it's right or wrong.
I'm not very sure, because also looking at the one after the shortest job first,
Okay.
that there'd be distinction between CPU bound and IO bound.
Okay, so you understand now that what is the difference between CPU bound and IO bound? Abid.
I thought that the CPU bound processes are longer than IO bound processes.
So I'm asking that at least you understand now that what is the difference between IO bound process and CPU bound process?
Yes.
Okay. So anybody else? Okay, fine. So in multi-level feedback queue, we have multiple queues. Okay, so if there are multiple queues and we have grouped the processes based on their characteristics, then obviously CPU bound processes will get high priority. Okay, so in comparison to round robin, FCFS, SJF, and SRJN, as they have defined, shortest remaining time first. So those are not dependent on the particular property, whether it is the CPU bound property or IO bound property. But multi-level feedback queue is dependent on the process characteristics. So that's why the priority will come into picture depending on the process characteristics. Last one, the infinite postponement. Infinite postponement is a concept kind of starvation. Starvation means somebody is dying in the lack of food, or there is a lack of resources. Because in daily life, we define the thing of starvation that somebody is not getting food. And in terms of system, in terms of processes, we define starvation as that processes are not getting the time to get executed. So they are starving. Okay, so infinite postponement is the same thing, kind of starvation. So when we are considering the concept of round robin, obviously infinite postponement will not be there, because every process is getting their turn after a fixed time quantum. Okay, so if there are 5 processes in the system and there is a time quantum, fixed time quantum of 2 milliseconds, then each process will get their turn at means maximum after 8 milliseconds. Because after 4 processes, definitely its turn will come. Okay, clear? In FCFS, obviously it will not occur, because one by one all the processes will get executed, and finally, okay, it might be late, somewhat late in comparison to round robin, but definitely your turn will come. Okay, in multi-level feedback queue, it may occur for CPU bound processes. For example, there are so many processes, those are CPU bound. So most of the time they will get executed with CPU, because they are spending their most of the time with CPU. So then input output processes may get starved for very long time. Okay, for shortest job first, it also may occur, because there is a possibility that there is one job that is which is supposed to have a total burst time of 10 milliseconds, and there are other jobs they are supposed to have the burst time of 4 milliseconds, 2 milliseconds, 3 milliseconds, 5 milliseconds. So okay, now all the jobs got executed which were shorter than the 10 millisecond job. But when its turn was supposed to come, just before that, another process came which was having less burst time than 10 milliseconds. Then again its turn will get delayed. So whenever the turn of 10 millisecond job is supposed to come, every time some new job comes, some new process comes into picture that is having the less burst time than 10 millisecond job. So in this particular scenario, that particular 10 millisecond job may get starvation kind of situation, because its turn is getting postponed, and it is obviously system dependent, that its turn may come or will never come. Okay, so starvation or the infinite postponement may occur in shortest job first, and the similar reason do stands for shortest remaining job first. Okay, now we are going to another 2 criteria, that is overhead and CPU bound. Okay, now I am expecting the explanation of overhead point from you guys, because it is very simple. And overhead means what are the problems, means what are the extra burden that we are having in a particular kind of scheduling algorithm. Okay, whether it will be more or it will be less, means the overall management of the scheduling algorithm is a burden. If yes, then it is more or less. Okay, so that is overhead. So tell me why the round robin is having low overhead. Guys, I'm reaching to you.
Yes, Professor. Can you just repeat once in short what is overhead meaning?
Overhead means it's a kind of burden, means a normal way, means what is the literal meaning of overhead? Literal meaning of overhead means kind of burden or the pressure that you do have. Okay, so similar way, what is the burden in case of round robin in its management? So when we say overhead, means what are the additional responsibilities or the other complex things that round robin is supposed to manage? Means its behavior is complex or simple. That is overhead.
Okay, so Professor, like how I think of this is round robin, there is not much of decision to be made because it's directly one after the other. First come, first serve also is like that. But when
Yes.
you have the other ones like multi-level feedback queues, shortest job first, then shortest remaining job next, here
Yes.
some sort of computation is required to decide which process should be coming first and which should be next. So more
Fine.
resources are spent to that. So that's why that creates some more burden on.
Yeah,
Yeah.
great. I think it's a complete explanation because as there is written that in multi-level feedback queue, we are supposed to analyze the characteristics of the processes and the underlying scheduling algorithms. Then in shortest job, first every time after every execution, we are supposed to again recalculate that whichever which particular process is supposed to have the minimum burst time. Okay, in the shortest remaining time, that is more complex in nature, means every time you have to maintain the minimum time period that is remained for completion with respect to every process. So means in terms of FCFS and round robin, you are not supposed to do any particular calculation. In round robin, even you need to maintain the time quantum, that after every time quantum, you are supposed to jump to another process. But in FCFS, you don't even need to consider the time quantum also. That's why FCFS is simplest. There is lowest burden. Now there is final point, that is CPU bound. CPU bound means obviously there is no distinction. It is same with respect to IO bound, as we saw here. You can see the IO bound. So there is no distinction. Kind of similarly CPU, there is no distinction between the IO bound or CPU bound processes with respect to round robin FCFS. But obviously with respect to multi-level feedback queue, it is because the process characteristics come into picture, but no difference in shortest job or shortest remaining time first. Lastly, we are going to, not lastly, that is second point, that is the second module of today's focus, and that is deadlock. So deadlock, when we say deadlock, then it's a lock where your situation is a kind of, you are in a dead state. Means you are not making any sort of progress. And then when you are not making any sort of progress, then you are kind of in a dead state. Now, when we are saying that it's a deadlock, what exactly it looks like? Then in the figure, you can see that it's a deadlock situation. See it for 10 seconds and then analyze it.
Professor, can we get a quick break if possible, like a few
Yeah,
minutes, and
sure.
then we can come back?
No issue, no issue. It's a 5:25. We take 5 minutes break.
Thank you. Thank you.
Right. Okay, guys, 5 minutes over. We are going to continue. So in this particular diagram, you can see that Deadlock's situation in OS looks like this. It's a very simple model. Here you can see that there are two processes and there are two resources. Okay, so resource might be in terms of there is some memory location that processes are supposed to access, like we discussed the concept of critical section in last class. Okay, or it might be some input output device, or it might be some other kind of important valuable information that is stored somewhere else. Okay, so resource is some sort of input output or memory resource. Now processes are the jobs, so those are in system in ready state or in waiting or in execution state. Now two processes, two resources, simplest model, two process deadlock model. So here you can see process 1 is holding resource 1, means resource 1 is already been assigned to process 1, and now process 1 is requesting for resource 2. Okay. Similarly, process 2 is having the control of resource 2, means resource 2 is already assigned to process 2, and now process 2 is waiting for resource 1. Okay, so it is a cycle, means in simple terms, process 1 is dependent on process 2 and process 2 is dependent on process 1. So when this sort of situation happens in a particular kind of system, then that particular system is supposed to be called that particular system is in deadlock. Now system is in deadlock means that those are two processes. If there are only two processes in the system, then we will say that system is in deadlock. But if only some of the processes of a particular system are in deadlock state, then system is not in deadlock state, means the system is not in unsafe state, but that those two processes are in unsafe state. So that's why by using some sort of mechanism, kind of deadlock prevention or avoidance kind of mechanism will come into picture, means we will preempt one of the process and we will break this particular cycle. So creation of the cycle assures that there is a deadlock, and breaking that particular cycle will assure us back that now there is no deadlock. Okay, so what we discussed here is that. So we discussed what is the deadlock. Okay, now when a deadlock happens in a particular system, so there are 4 specific conditions. If all these 4 conditions, there is not that if any one of these is not present, still there is deadlock. All of these 4 conditions must be present in a system. That's why then only we can say that there is a deadlock in the system. First concept, that is a mutual exclusion. In the last class only, I discussed the concept of mutual exclusion. Anybody? What is the meaning of mutual exclusion? Guys, you can listen me. Hello.
Yes, Professor, we can hear you. I don't remember exactly mutual exclusion.
Okay. Mutual means when it is related to mutual, means both parties, then it is mutual. Exclusion obviously means you are not sharing the common space. That is exclusion. For example, when there is a news flashes on a particular TV screen and there is a written under that particular section or something like that, that it is exclusive in nature. Okay, so mutual exclusion means that there is something that you can only access in an exclusive way. Then that particular phenomena is called mutual exclusion. Means you can see here, when resource 2 is owned by process 2, then process 1 cannot gain entry to resource 2. So it means what? That resource 2 can be only accessed in an exclusive fashion. Similarly, the same kind of condition do have get applied for resource 1. So process 2 is waiting for resource 1. It cannot take resource 1. It cannot have the access of resource 1. Why? Because it is already being used by process 1. Unless process 1 will leave resource 1, process 2 cannot have its access. So in this way, it is means resources are being shared in mutually exclusive fashion. Okay, that is mutual exclusion. Second is hold and wait. Means processes are supposed to hold a resource and they are asking for another resource. Then it is the second condition, that is hold and wait. Third condition is that no preemption, means you cannot take the resources back from a particular process forcefully. That is no preemption, means without just before the completion of a particular process you cannot take back its resources. That is no preemption. Lastly, circular wait, means there should be a cycle, means there should be a cycle of dependency among different processes, then it will be circular wait. Now see, these four conditions are compulsory to have a deadlock in the system. If any one of these four conditions is not present, then obviously there is no deadlock. For example, first condition, mutual exclusion. For example, you allowed the processes to have the common access of the resource at any time, means there is no exclusive fashion or something like that. Then will there be a deadlock? No. Why? Because then process 2 will not wait for resource 1. It will have the resource 1, means it will have the common access, means process 1 and process 2 can share the resources. They can have the access of same resource at the same time. Okay, then there is no mutual exclusion, means no deadlock. Second condition, hold and wait. If processes are not supposed to hold a resource and then ask for another resource, then there will be no waiting, because waiting happens when one particular resource is being assigned to another resource, it is using it, and at the same time that particular process is asking for another resource also. Then only it will help in cycle formation. Okay, so there is no waiting if we don't have the hold and wait condition. Third, there is no preemption, means if we allow preemption, means if we allow the system to forcefully take back the resources from the process 1, then system will take the forcefully resource 2 from process 1 and will assign to process 2. In that particular case, there will be no cycle. And finally, circular wait, means if there is no cycle, if there is no mutual dependency, then obviously there is no deadlock. Because if there is no cycle, if there is a cycle, means from where we started, there only we came back in terms of dependency, then only we can say that this cycle will never break. Why? Because everyone is depending on each other. So in this fashion, if there is no circular wait, then processes are waiting. Might be the scenario that processes are waiting for are dependent on each other, but they will progress, means they will get completed after a particular while. Why? Because the very last process in the cycle, very last process in the line, not the cycle, will complete its execution. It will release its resources. Then it's a dependent process will complete its execution, and in the similar fashion, all the processes will complete their execution. So circular wait means a cycle is a must. If there is no cycle of dependency, then obviously processes will make progress. And if they are able to make progress, obviously they will complete their execution. Might be after some time, means there might be some delay, but there will not be infinite wait. That's why deadlock will not be there. So when we are saying that deadlock might be in a particular kind of system, then we should talk about that what are the different possible scenarios that when we can have a particular deadlock. So we should try to avoid all those kind of scenarios. So there are two particular kind of possible ways to handle the situation of deadlock, that either we prevent it or we avoid it. Okay, now both terms look similar, but there is a kind of difference. Okay, so prevention is a kind of avoidance only. Normally in normal terms we say, but in terms of prevention, what we try to do, we try to not even allow the deadlock to happen in the system. Means we don't even allow the necessary conditions to happen in the system. So that's why under the prevention you can see that prevention blocks at least one of the necessary conditions. What are the necessary conditions? We saw just now that there is mutual exclusion, there is circular wait, there is no preemption, and there is hold and wait. There are 4 necessary conditions for deadlock. So if we block, means if we break any one of these 4 conditions, then there will be no deadlock. Okay, either we allow preemption, or either we allow sharing of the resources, means no mutual exclusion, or either we don't allow to hold and wait, and if we break the cycle, then there is no deadlock, means there is a prevention system in the system. So we can see that if we block any of the necessary condition of deadlock, then obviously there will be a state of prevention. Obviously now we are just breaking the conditions, so we don't need any future information, means like in case of avoidance, you can see, means you will not understand the concept of avoidance fully unless you will get an example. So in the next class we will discuss the Banker's algorithm. So Banker's algorithm will give you a full-fledged idea that how exactly we are talking about the future knowledge. So we are not supposed to access the future information in case of prevention. We are simply just, what we need to do is simply need to break one of the 4 conditions in case of prevention. And preemption is very frequent in prevention. Why? Because no preemption is one of the 4 conditions. And the simplest way to break a deadlock is to take the resources back from one of the processes. If we took back the resources from one of the processes, that process became invalid, means that process got either terminated, or we can say it got shifted to waiting state. Now there is no dependency because there is no cycle. If there is no cycle, there is no deadlock. Okay. And lastly, prevention doesn't need the future processes request information. Means you are not supposed to concern about that. What are the future requests of processes? Future request means the future process requests for resources. You are not supposed to worry about those. All those things are just which are just opposite to prevention. Those are needed in avoidance. Means you are supposed to ensure that system is in safe state. So you are supposed to manage that whether all the processes are supposed to get completed without falling into a trap of deadlock. Additionally, you are supposed to have the system resources information, means exactly what type of resources and how many instances of a particular resources a particular process will need to get completed. So in this fashion, you are supposed to have the futuristic information about the process request information. Okay, and the examples of prevention is pooling and some of the non-blocking synchronization algorithms. In case of avoidance, very popular and that is very important, that is Banker's algorithm. So that we will discuss soon. So we are going to talk about the third module of today's focus, that is multiprocessor scheduling. Multiprocessor, as we discussed, that there is a single processor. Till now, whatever we discussed, that is with respect to single process, means there is a single point of control. That's why we are having the concept of scheduling. But scheduling is not only the concept that is discussed with respect to uniprocessor systems. Scheduling is possible in multiprocessor systems also. Same thing is there. The only difference is that instead of having a single processor, now you are having multiple processors, means multiple line of controls. So there, as you can see from the diagram, there are 3 CPUs, okay, and there are their respective queues. Those are called local queues, and there is a common ready queue. Okay, so from ready queue means that is the ready processes in ready state. Okay, there are J1, J2, J3, J4 means job 1, job 2, job 3, job 4. Okay, instead of J1, J2, we should call them P1, P2. Why? Because those are in ready state, means those are if we call them ready queue, means if they are J1, J2, means they are the programs, simple programs in disk. But once they are in ready queue, or once they are ready, so as they have defined a local queue for separate CPU, so perhaps the local queue is their ready queue of particular CPU, and this ready queue is the ready queue of disk, and local queue is the ready queue of RAM. Okay, so from ready queue, J1, J2 will get assigned to local queues, and then that particular processor will take care of that particular job. So all the processes in the local queues will get assigned to the CPU, again depending on a particular scheduling algorithm. All the scheduling, like we discussed till now. Okay, so from the job pool, jobs will get assigned to local queues in terms of processes, and from their local processes, from their local queues, the processes will get assigned to respective CPUs. So first point means in multiprocessor scheduling, first point is very common, and that is obvious also, that is the presence of multiple CPUs. Secondly, load means obviously if there are multiple execution elements in the system, then load will be shared. In case of uniprocessor system, all the load is on a single processor. In case of multiprocessor system, the load is divided. Third one, complexity. Obviously, the load is divided, but the complexity is more. Why? Because if you are having more CPUs, you need to maintain more queues, more local queues you can see. Additionally, you need to maintain the synchronization mechanism between these CPUs. Among these CPUs, if you are having more than 2 CPUs, okay. So you need to maintain the synchronization, means the access of common resources. If there is some common space or common resources that all the CPUs are supposed to access, then again you need to maintain some sort of synchronization that if one processor is using that resource, another should not. Okay, so that's why the underlying architecture, the underlying structure, underlying functioning mechanism, that is more complex in comparison to uniprocessor. Now you can see there is the comparison between the symmetric multiprocessing and the asymmetric multiprocessing. So these are two very common types of multiprocessor schedule. Okay, so in symmetric multiprocessing, what you can see that there are 3 CPUs on the left hand side part of the diagram, and then those are trying to access, means they are supposed to have the control of process P1, P2, P3. But in asymmetric, you can see that individual component is taking care of individual process. It is not like that randomly some process will get assigned to some of the system. Additionally, you can also see that in asymmetric multiprocessing, there is a concept of master slave. Master slave means there is a one component that is supposed to be master of all other components. So all other components became slave. Okay, so based on the master's instruction, other processor, those are slave, will work according to the wish of master. So master will tell that you are supposed to have access of this, you are supposed to have access of this. So in this way, if you perform the functioning of a particular system, then that is a master slave system, means asymmetric. Asymmetric means there is no synchronization required because there is a clear-cut instruction out there. But when you have a common space, when you have the common resource, then only you are supposed to have the synchronization in picture. So as you can see, in symmetric multiprocessing, there is a common memory, there is a shared memory, there is a common memory space where all the processes resides. So that's why processor 1, 2, 3, anybody can access that particular process pool. So that's why a synchronization mechanism is required to avoid the chaotic situation. Okay, so in asymmetric, as you can see from the points that the master slave concept is there, obviously it is simple. Okay, and why it is simple? Because we don't need the synchronization mechanism there, and it reduces the need of data sharing also, because we don't have the synchronization mechanism, so we don't need to put the mutex and the synchronization variables into picture. All these things we will discuss in detail later. Okay, so synchronization helps to manage the behavior of a shared memory in an easy way, and that we do need in case of symmetric multiprocessing. So each processor is self-scheduling. Each processor will take care of its own scheduling in case of symmetric. But in case of asymmetric, master processor will take control of the scheduling of all slave processors. Okay, so slaves are not supposed to make decisions. Only master is supposed to make decisions. Okay, so that's why there is a master slave concept. All processors are not self-scheduled. Now, in symmetric multiprogramming, the complexity is more, obviously, because there is a synchronization concept. And finally, there is a common memory space. So that's why more data sharing is there. I think there should be no confusion. If there is any confusion till now, please do let me know. Fine. Okay, so moving forward, these are the references, and that's all for today. So it's been We do have 5 more minutes. If anybody wants to have some discussion or have some question or answer, please.
So, Professor, I was thinking up an example of a deadlock.
Yeah.
So, is this
Okay.
fine?
Yeah. Speak.
Yeah. So, I thought about, like, suppose there's only one block of memory.
Yes.
And that block is assigned to process 1.
Yes.
But process 1 requires an input from process 2.
Yes.
Some data input.
Yes.
But process 2 is not getting memory.
Yes.
Because it's already given to process 1. So is this a deadlock?
Yes, obviously. Because see here, but the condition that you told me, that is kind of subjective. How it is subjective? Let me explain to you. For example, process 1 needs a data input from process 2. It doesn't need any resources that is held by process 2. So, for example, the data that is supposed to be taken from process 2 is not dependent on that resource processing. Okay, so process 2 may give its data input to process 1 and it will complete its execution. Okay, but suppose if process 2 data that is supposed to be given to process 1 is dependent on the resource processing that is held by process 1, then process 2 cannot give data to process 1 until it takes that resource control, perform its execution and have that data value and then pass it to process 1. Understood?
Right.
Okay, so there is always a scenario, means what kind of data dependency, means doesn't matter whether it's a resource dependency or data dependency. If there is a dependency, there is a loop. If there is a loop, then obviously there is a possibility of deadlock. So all the things, because normally we discuss deadlock with respect to resources only. So this sort of questions do come in mind, that what if resource dependency is not there, data dependency is there, but that data might be dependent on the resource users. So in that case, it is deadlock only. Any other question? Okay, guys. Thank you for your time. Today, it completed within time. Okay, great. Enjoy your weekend. For any sort of questions, so do let me know via mail. Okay, thanks. Thanks for your time.
Thank you, Professor.